This question is exciting. This question is a VSEPR structure. So this is going to take everything that we have learned and start to put it together. Now, this is also kind of a complicated question. So you'll see that there are 5 different rows. And so we are going to look at all 5 of these. So the first thing we're going to do as we move our way across is we're going to look at pH 3 and how many valence electrons are there. So there are 5 plus 3, that equals 8. And for simplicity, I'm going to have to zoom in on these so that we can actually see what's happening. So we have the phosphorus in the center for a Lewis dot structure. We're going to put our phosphorus. We're going to connect our 3 hydrogens. So we have now used 6 of our 8 valence electrons. The other 2 will go here. To determine the VSEPR, we know that it's related to the steric number. Phosphorus has 4 things connected to it. That makes it a steric number of 3. That also makes it base tetrahedral. So put our phosphorus in the center. Then you can put your hydrogens in your lone pair. It doesn't matter where they go on here, they are all equivalent. Now, it gives you the base geometry. That's related to the steric number. The molecular shape is what does it look like because you can't see electrons. So in this case, it is trigonal pyramidal. Or trigonal pyramidal. Either one is fine. So the next question asks, the next part of this, it's going to ask about the dipole moment. So dipole moments, there's 2 things to note. One, if the bond is not polar, the molecule can't be polar. If the bond is polar, that doesn't mean that the molecule is polar. So to determine if it's polar, we're going to use electronegativity. So for P and H, in this case, you would look at the electronegativity trend, which is provided for you in the equation packet. So it's 2.1 minus 2.1. So that makes it a non-polar bond because they're equivalent. That should be a 1. And so in this case, there is no electronegativity difference. The bond is not polar. The molecule is not polar. So if we have a steric number of 4, that means 4 orbitals were combined. That means that it is sp3. So this is the format that we're going to use to fill out the rest of this table, which is going to take us a minute. So for BRF5, we have 7 plus 5 times 7. So really 6 times 7, and that gives you 42 valence electrons. Put your bromine here in the center. I'm going to just start adding my fluorines. And now I'm going to just start putting in all of my lone pairs. I know it's taking a while. So if you were to go back and count or multiply 8 times 5, that gives you 40. We have 2 left over. So this tells us that we have a steric number of 6. So we have a bromine in the center. And it's going to look like this. So we know it's octahedral because it's steric number of 6. So now we're going to put on our fluorines. And in this case, we want to make sure that we show all of our formal charges and lone pairs. A good general rule of thumb is if the molecule is neutral, there aren't usually formal charges. So when we lose one of our substituent atoms here, this is now a square pyramid. And so it looks like that. So next, we're going to ask about polarity. So we have our Br, F bond. So F, fluorine, is 4.0, and bromine is 2.8. So this means that they're a difference of 1.2, which is in the polar range. So the dipole goes towards the more electronegative. So now we have to ask ourselves this question. Is the molecule polar? And this can get kind of hard. So as we draw in our dipole moments, I'm just going to make this kind of messy. So I'm going to just draw those. You can see that in the two fluorines that I've highlighted blue, those two dipoles are opposite of one another. So technically, those two and the dipoles along this axis are all going to cancel out. However, this is a polar bond, and there is nothing on the other end to cancel it out. So this is, yes, a polar bond, and yes, a polar molecule. And so the last part asks us for the hybridization of the central atom. And because there are 6 orbitals, it's sp3d2. So as you can see, these take quite a while, and they will be like this on the exam. So next, we have BrO2 minus. I would like to report that this minus should be up higher, but the formatting kind of gets crazy. So we have 7 plus 2 times 6 plus 1. You get an extra 1 for the negative charge. That gives us 20. So we're going to put our bromine in the middle. I'm going to connect my oxygens. So I'm going to start by using 16 of my electrons. And now I've used all my electrons, so all 20 have been distributed. However, we have a negative charge. So let's look at the formal charge. So the formal charge for oxygen is 6 minus half of 2 minus 6. So we have negative 1. So we have a negative charge here and here. For the bromine, it's 7 minus half of 4 minus 4. And so that gives you plus 1. So we have a positive charge here. When we think about formal charges, this is a pseudo-correct element. However, what about if we made a double bond? Because then by removing an electron pair from here, putting them here, we could make the formal charges of 1 oxygen and 1 bromine go away instead of having all of these atoms have charges. So in this case, what we're going to do, and I'm going to erase some things here. So I'm going to erase this negative charge and this positive charge. And what I'm going to do is I'm going to give it a double bond here. So the formal charge with the oxygen at the top just stays. For bromine, it's 7 minus half of 6 minus 4, which gives it 0. For this oxygen, it is 6 minus half of 4 minus 4, and that gives it also 0. So it is a preferred structure where it looks like this. So there's not really enough space on this table. For here, from the bromine, if we want to draw our VSEPR structure, we know that there are 4 things. Even though one of them is a double bond, we're going to have our bromine. Just happened here. Of our bromine. So now we have our bromine, and we need to decide where things go. Personally, I like to put my double bond in the plane of the paper. So from here, it's going to have two lone pairs on it. We're going to have a lone pair here, here, and then we're going to put our other oxygen here, and it has a negative charge. So in this case, it is tetrahedral. Sorry, we're having all kinds of like line width problems, as you can see. So we have tetrahedral, and the other is bent. So now let's move into the more difficult. So we have a bromine oxygen. Bromine is 2.8, and oxygen is 3.5. And so this is a 0.7. So that does give you a polar molecule. So it is yes, polar. And because these two don't cancel out, in fact, the molecular dipole will go in roughly that direction. And so it is yes, polar. If it is a steric number of 4, which is what we have, we know that it's base tetrahedral, so it has to also be sp3. So we've done 3 rows. So let's look at the next one. So we have arsenic, which has 5 electrons, plus 3 times 1, plus 7, minus 1, because we have a positive charge. And so that gives us 14 valence electrons. So we're going to put our arsenic here in the center. That's a mess. We're going to connect our hydrogens and our chlorine. And so we're going to give this octet. So we've used 2, 4, 6, 8, 10, 12, 14. There's all of our electrons. So who owns the positive charge? So we're going to start by calculating that for the arsenic. So for the arsenic, it's 5 minus half of 8 minus 0. That gives you plus 1. So this is going to have a plus 1 charge. So we know that this has a steric number of 4, which makes it tetrahedral. It does not have any lone pairs associated with it, so it's tetrahedral. So for arsenic, we're going to connect our atoms. I'm going to put our hydrogens around. Don't forget your formal charge. So now we need to move on to the next column, polarity. So we have 2 bonds in this case. So we have the arsenic hydrogen bond and the arsenic chlorine bond. The arsenic hydrogen bond is 2.0 and 2.1. So this is nonpolar, but we have a chlorine bond. And so in this case, the chlorine is 2.0 and 3.0. So that is polar. So yes, that bond is polar. And because we have a polar bond, we have a polar molecule. So yes, the whole molecule is polar because this chloride is polar. So what about the hybridization? So it is also sp3. So far, what we've seen here is if we count the valence electrons, we can then figure out the Lewis dot structure. So let's look at ClF3. So we have 7 plus 3 times 7. That gives us 28 valence electrons. So we have our chlorine. We're going to put our fluorines around it. So we've now used 24 of our 28. So we have 2 lone pairs left. You can really put them anywhere you'd like on your Lewis dot structure. So this gives us a steric number of 5, which is new. We haven't seen it yet. So this is trigonal, bipyramidal, in the molecular shape, we're going to have to draw this structure. So we have a chlorine in the center. That's terrible looking. So let's try that again. So we're going to put our chlorine in the center. And for a steric number of 5, it looks like this, where we have bond angles of 90 and of 120. So we're going to put our fluorines here. And our 2 lone pairs. So if you look at this, you can see that it kind of makes a T. So it is T-shaped. So the next question asks about polarity. So the chlorine-fluorine bond, so we 4.0 for fluorine, and chlorine is 3.0. So this is a polar bond, yes. And so the question is it a polar molecule? So the two fluorines in the axial position, the ones that go up and down, cancel each other out. But we do have a polar bond that is not canceled out. That says, yes, this is a polar molecule. And so our last question asks about the hybridization. 5 orbitals combine to make this. We have 1s, 3 p's, and 1 d to give us a total of 5 for the hybridization. So this was a lot. But the reality is, in order to determine the hybridization, it's based on the steric number. And the steric number is based on how many things, whether it is double bonds, electron pairs, whatever that is, how many things are connected to the central atom. From there, you can figure out the base geometry, the molecular shape, the hybridization, and the VSEPR. As long as you can come up with a Lewis dot structure based on your number of valence electrons.